Thanks to you all for being here after yet another fabulous meal last night. And thank you, Zaya and Maurizio, for putting this all together in this fabulous place. It's very, very nice to be here in Italy. So I want to talk about what physics can tell us about consciousness. And the brief message, as you all know, is that physics basically tells us two things. One, there's no such thing as objective material objects. And two, consciousness has to be fundamental. So we'll talk about that a little bit. But then what I really want to focus on in this talk is something new, which is what can consciousness tell us about physics? And there's, of course, a trivial answer to that question, which is whatever we know about physics, we learn because we're conscious. If we weren't conscious, we wouldn't know any physics at all. So obviously, consciousness tells us everything about physics. But while that's clearly true, it's not very helpful. So what I want to ask is, what can very specific assumptions about consciousness allow us to predict about the physical world? Can we actually make assumptions about consciousness and use those assumptions to derive predictions that we can then go out and test in the way that scientists in general go out and test stuff? Because that's how science works, by making predictions and seeing if they're right. Trying to figure out why they're wrong, usually. So that's what the second two-thirds of the talk will be. So anyway, let's start with some physics, and let's go back to Newton. So here we are in the late 1600s. Newton, based on the work of Kepler and Galileo and Tycho Brahe and the rest of those interesting late Renaissance people, really brought into the community the idea that we can describe nature using mathematics, and that description is productive in the sense that that description allows us to make predictions that we can then go out and test, and of course engineer technologies of various kinds that do useful stuff, like dig big holes in the ground, for example. So this is just Newton's second law, that force equals mass times acceleration. These are mathematical concepts, abstract concepts. And Newton phrased all of this against the background of a fixed space and a fixed time. And space and time for Newton were objective. So you can think of it in the standard way that we all learned in elementary school, that there's this background in the world that consists of space and time, and stuff happens in that background. So let's fast forward about 100 years to Immanuel Kant, this guy who really was a natural philosopher in the best sense of the word. He was interested in everything, from ethics to politics to psychology, physics, mathematics, the works. He was just one of those people. And here's an interesting thing that he said: space and time are just frameworks that the mind uses for organizing experience. And this was the key underlying idea in Kant's approach to metaphysics, that there isn't this objective space and time out there. Space and time is something that we, by thinking, impose on the world. Okay, let's fast forward another 150 years to Einstein, who turned those ideas into a real mathematical structure that we could use to make predictions. So, I don't have my cell phone with me, but this has one. There's a GPS in here, and that GPS will tell me where I am to an accuracy of about 1 meter. That much, right, from space. Now, the only way that works is because we know general relativity. If you try to do that calculation, satellite to me, using Newtonian classical physics, you can get me accurate to about 100 meters, roughly. General relativity is much better, 1 meter. So this is a real practical theory that comes from this idea that space and time aren't objective entities, they're ways that we think. And it makes you wonder, right? Remember, Einstein hated quantum theory. Einstein once famously asked Abraham Pais, "You mean they think the moon isn't there when you look at it?" Einstein was dedicated to the idea that objects, like the moon, are objective. In the classical, good old, they exist, whether you look or not way. So why did Einstein think that and still think that space and time aren't objective? Well, that's a nice historical mystery, right? So let's move on to these guys who have been quoted a lot in this meeting. Here's Heisenberg, and he says, what we observe is not nature, not an objective existing thing, but rather nature exposed to our way of asking questions. So remember, Heisenberg formulated all of quantum mechanics in terms of operators, mathematical entities that represent measurements. He said you act on the world in a certain way and it gives you an answer. You act on the world in a different way and it gives you another answer. And that's what physics is a theory that tries to put those answers together. So here's Schrodinger, the other real founder of formulations of quantum mechanics, saying, look, the plurality that we perceive is just an appearance. So the separateness of things is just an appearance. That's not reality. And Schrodinger introduced the concept of entanglement, which is the key concept of quantum mechanics, that says the entire world is one thing. And oh, by the way, you're part of it. Right? So it's not the world out there that I'm looking at is one thing. That's true. But the world out there that I'm looking at and me is also one thing. So what I'm doing and what the world is doing are intimately coupled. There's no such thing as me doing something independently of the world. And there's no such thing as the world doing something independently of me. Why? Because we're one thing. There is no independence. So that was Schrodinger. Okay. So this really challenges this Newtonian picture. I mean, by the time we get to the mid-20th century, physics is totally different. And even the mathematical language is different. So now I want to mention some people that you may not have heard of. This is Willard Gibbs, an American, and this is Ludwig Boltzmann, a German. And they invented in the late 1800s the part of physics called statistical thermodynamics. And statistical thermodynamics is the part of physics that allows us to make predictions about large numbers of more or less identical things that we can't look at individually. Like, for example, air molecules. And statistical thermodynamics is where you get concepts like entropy. So it's highly improbable that all of the air molecules in this room were to assemble into a small drop of liquid nitrogen in that corner right now. And that would be a bad thing because we'd all die. So that's very, very, very improbable, and statistical thermodynamics tells us why. Now this is Claude Shannon, who you may have heard of as one of the founders of information theory. And this is Rolf Landauer, one of the main developers of information theory as applies to quantum computation. And the message that all of these people give us is that information itself is physical. And what that means in practice is that getting some information requires using energy. And the energy has to come from somewhere. So we all had breakfast. So we ingested a vast amount of energy. And that allows us to get information. And if we didn't eat, we'd very quickly become incapable of getting more information. So getting information requires using energy. And this is the theme of this talk. What happens when you take seriously the idea that getting information requires using energy? Okay. So now we're going to go on to John Wheeler, who made his famous pronouncement of it from bit. And what Wheeler meant by this was, look, there's really no stuff. It's just information. What physics is about is information. and how information is structured. And this, what appears to us as a physical world, is just a construct of this information that we create by asking the world questions. The other thing that Wheeler said quite nicely was, no question, no answer. If you don't ask questions, you don't get any information. Okay, so this is all of this thinking takes place against a background of an assumption that's very seldom stated explicitly. And the assumption that's made across not just physics but all of science is that we are not special. Humans are not special. We have a point of view, but it's not a unique, special, weird, different point of view. If there were other observers elsewhere in the universe who had a completely different point of view, they'd see more or less the same kind of universe we do. And with that assumption, science becomes completely idiosyncratic, so it doesn't really make any sense. So science has to assume that what we see is not completely unique to us, that other observers could see roughly the same thing. Now, the way that assumption gets fleshed out is with the claim that measurement and observation are just physical interaction. So if you read the literature, you'll find statements like, the observer is just a physical system that is entangled with the system of interest. So the observer is just some physical system or other, you don't have to specify what kind, that's interacting with, and hence in quantum theory, entangled with, whatever it's observing. And that entanglement is what allows information to flow back and forth. Now, that means in the language of physics, which is by intention non-ambiguous and very precise, that observation is exactly the same thing as physical interaction. It's not a different aspect of physical interaction, it's the same thing. Those are just two words for the same kind of event. Well, what does that mean? That means that all systems are observers, right? If observation is just physical interaction, then, this is physically interacting with the table. So this is an observer, right? It detects the table. And the table's an observer. It detects the cup. So all systems are observers. So if consciousness has something to do with observation, consciousness has to be fundamental. And most of us, at least, believe that consciousness has something to do with observation. If I wasn't conscious, I wouldn't be observing anything. So if observation is interaction and consciousness is important for observation, then everything must be conscious. Now, of course, lots of people don't, okay, well, this is the next sign. So what? Right? Most scientists, I would say, are epiphenomenalists about consciousness because they can't answer this question. And this is, I would say, the most important question to ask about any scientific idea whatsoever, and maybe all ideas, period. So what? Interesting idea, maybe. But what's it good for? What does it actually allow you to do? Okay, so that's what the rest of the talk's about. What can consciousness, and in particular consciousness being fundamental, tell us precisely about physics? So first let's do a warm-up exercise. And the warm-up exercise has to do with answering the question, what is quantum mechanics? What does it mean to say something is quantum? What does it mean to say something is a quantum system? Okay, so let's start. Everything's an observer, so in particular, this nice little biomolecule called rhodopsin, which there's tons of in your eyes, is an observer, because everything's an observer. And we know a lot about rhodopsin. Rhodopsin detects light. When it detects light, it changes shape. And that's the first step in you knowing that there's a light out there from a biochemical point of view. Rhodopsin changes shape, and you say, oh, light, cool. Okay. So let's assume that rhodopsin is an actually optimal observer thermodynamically. And that means something very precise. It means that the amount of energy that rhodopsin needs to spend is exactly this. The 0.7 converts you to bits. It's just the natural log of 2. And then this number kt. K is a constant called Boltzmann's constant. Remember, Boltzmann invented statistical thermodynamics. And T is the temperature. And part of statistical thermodynamics say to get one bit of information, one yes, no answer, light, no light, right? Left, right, whatever. One bit requires 0.7 kt if you're optimal. It can require more, but it can't require less. So now let's do some simple math. We can make measurements on rhodopsin in the lab, and we can say, how long does it take rhodopsin to detect a photon and change shape? And the answer is about 200 femtoseconds. So a femtosecond is 10 to the minus 15 seconds. It's a very, very short period of time. And 200 femtoseconds is the time it takes, typically, for electrons to move around in big molecules. So this is real fast. And it turns out if you look at photoreceptors in plants, carotenes, for example, they take about the same amount of time to receive light and change shape. So chlorophyll components, same, roughly speaking, amount of time. So that's really cool. We know how long it takes to respond. And there's a concept in physics called action, which is just energy times time. So we know a time, 200 femtoseconds. We know an energy, 0.7 kt. So we can calculate this number, which is the action. And so we just plug in the numbers at room temperature, 37 degrees. That's actually body temperature. And you get a number for the action, which is 6 times 10 to the minus 34, so a tiny, 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 tiny number, in units of joule seconds. Now, a joule is the energy of a 1 kilogram object moving at 1 meter per second. So this is not a funny kind of ultra-microscopic atomic theory concept. It's good old Newtonian physics, billiard ball kind of concept. I mean, a joule is like, shit. It's like that much energy. Hopefully I haven't broken this. No, very good. So the optimal action to record 1 bit of information from the world is that. We just calculated it. And if you're a physicist, that's a really familiar number. It's Planck's constant. So by doing some simple thinking about rhodopsin being an observer, we've managed to calculate on the back of an envelope what Planck's constant is, right? The key number in quantum mechanics. So that tells us something. Planck's constant in quantum mechanics is the quantum of action. It's the minimal amount of action to do anything. So what we figured out is what it really is the minimal amount of action to get 1 bit of information and do something with it, right? Change shape. So that tells us that's what quantized in quantum mechanics is not something weird about atomic orbitals or spin or anything like that. It's just getting information that's quantized. So quantum theory is really just a theory of getting information. And what's quantized is getting information. So quantum theory is a theory of measurement. It's a theory of interacting with the world to get information. It's not a theory of the measurement problem. The measurement problem is an artifact of thinking of the theory in the wrong way, not as a theory of how observers get information. So I would argue that quantum theory isn't spooky, it's not mysterious, it's very simple. It's just a theory of how you get information. And it tells you how much energy you have to spend to get information. And it reminds you that that energy has to come from somewhere. So when you take energy from the environment, you've changed the environment. So the uncertainty principle is not surprising. Of course you change the system you're looking at when you interact with it, because you're sucking energy out of it. Well, that changes it. No surprise. Okay, so that's quantum theory, and we can talk about that later. But what I really want to focus on today is a real question in physics and see where we can get with a real question in physics. And this is the question of dark energy. You've probably all heard of dark energy. It's very mysterious. It pervades the entire universe. We can't see it. We can't detect it. We only know it's there because it controls the rate at which the universe is expanding. And we can measure that. And so it's an extremely important theoretical number to say how much dark energy is there. And you've probably heard, if you've heard any of Manas's talks at previous meetings, that the most straightforward way to calculate the amount of dark energy in quantum field theory gets it drastically wrong. So it gets it wrong by 120 orders of magnitude. Okay, now that's an absurdly, stupidly huge number. There's no way to even conceive of that number. And here's the problem. This is Einstein's equation in general relativity. And this side is about how curved space-time is. And this side is how much matter is around. So this just relates curvature of space-time to matter. And that is the cosmological constant, that number, upside down lambda. And quantum field theory, gets it wrong by that much. Okay? So the first 12 of these is a trillion. So this is like a trillion 10 times. That's how wrong it gets it. Okay, so how do we know? We send up the Planck satellite. We spend tens of millions of dollars. We measure this number. And the dark energy density is known very precisely. It's about 6 times 10 to the minus 27 kilograms per meter cubed. So a meter cubed is like that. And a kilogram, I weigh about 100 kilograms, so that's a very small fraction of my weight. But if you think about the whole observable universe, which has this volume, it's about, we can see from here, 10 to the 20 some odd meters. That's the end of the observable universe. I mean, there's probably infinitely much more of it that we can't see, but that's how much we can see. And the observable universe has this volume. And the Planck satellite tells us that we take an average 1 meter cubed sample out of that observable universe, then there's this much effective energy in it that's dark energy. And that's what controls how curved the universe is, how fast it expands. Okay, so how can we calculate that? Let's assume that observers are everywhere, that all of space is pervaded with observers. And let's assume that they can at least all see the same things. Well, they can really only see the same big things because most of them are out there in the middle of empty space, right? So what can they see? They can all see the same stars. So what basically we're assuming is that the stars have objective positions, that any observer any place would agree that the stars are in the places they're in, regardless of the point of view that we look at them. So here's what a star field looks like for Hubble. You'll notice that this is not just a gray blur, which quantum theory says everything's smeared out over the whole universe. These stars are all in particular positions for us, so let's just assume they're in particular positions for everybody. Okay, and let's assume that there are 10 to the 25th of them. I mean, people count stars by counting galaxies and counting the average number of stars per galaxy and so on and so on. And the numbers are around 10 to the 23rd, 10 to the 24th, but they keep going up. So let's assume that they're 10 to the 25th. So maybe we're assuming that there are 10 to the 24 stars and the rest are planets or something like that. But these numbers are very back of the envelope. And let's assume that they're located classically to a particular accuracy. So we know the position of the sun to an accuracy of about 10 kilometers. We don't know it better than that. So let's assume that's the accuracy to which things are objective. Okay? So these classical positions are just information. You know, they're the result of observation. So now we do some math. We just divide the volume up into little cubes, and we say, how much mass, how much information is encoded in each of those cubes? Well, if they're 10 to the 25th stars, each cube has to say, that one's not there, here, and that one's not 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 here, 10 to the 25 times. And some of the cubes every now and then say, oh, stars, there's a star here, it's this one. So every observer can know by examining any one of these little cubes whether there's a star there or not, and if there is, which one it is. So that gives us an amount of information, and it's 4 times 10 to the 93 bits. It's a whole lot of information. 10 to the 93 bits. So now we've got bits. We know that we have to burn 0.7 kT to encode that bit. So we can say, okay, each of these little boxes has to burn that much energy to encode its 10 to the 25 bits. We can add all that energy up, and that's how much energy we get. 3 times 10 to the minus 27. So maybe that number looks a little bit familiar. We've just calculated the cosmological constant, right? And we got 3 times 10 to the minus 27 instead of 6 times 10 to the minus 27. But that number is accurate to a trillionth of a trillionth, about a tenth of a trillionth of a trillionth of a percent. So that's a really good calculation. We got the order of magnitude right, as opposed to being 120 orders of magnitude off. Now, were we to assume that the stars were localized classically, not to a box that's 10 kilometers big, but to a box the size of the Planck length, which is where everyone says that's where all the interesting physics is, down at the Planck scale. The Planck length is about 10 to the minus 35 meters, so many, 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 many times smaller than a proton or a quark or anything else we know about. If we insisted that the information was encoded that finely, we'd get a number that's 10 to the 117 times bigger. So I suggest that the reason quantum field theory is so wrong is that it thinks the information's coded down at the Planck length. And that's how the quantum field theory calculation actually works. It looks at the energy density at the Planck length. So it assumes that you can have classical information down there. But maybe that's wrong. Maybe you can't have any classical information down at the Planck length. And this certainly suggests that that's true. So in the last few minutes, what I'm going to do is what any physicist would do here. They would say, what does this mean? Well, it suggests that dark energy is just the cost of making things classical. But we've assumed that the whole universe is made of observers, and we've assumed it in a particularly bizarre way, right? We've thought so many stars and this kind of observer and all that. So let's try to calculate it differently. So many of you are familiar with Don Hoffman. He's talked at lots of SAND meetings. Last year, he and Chetan Prakash published something called conscious agent theory. And what they're trying to do is develop the simplest possible theory of what could be conscious. And the formal theory looks like this. A conscious agent is a little thing, and it can perceive, P, it can make decisions, D, and it can act, A, and when it does an action, then something happens, and so it perceives something else, and then it makes another decision, takes another action, perceives something else. So they call this a PDA loop. And the nice thing about this way of representing agents is you can combine them in arbitrary ways. So if you put 2 of them together, you can say, okay, the first one sees what the second one does, and the second one sees what the first one does, and information just flows in a nice little loop between the 2. So this is 2 agents in interaction. So let's make this assumption. Let's imagine that space-time is actually created by these conscious agents that Don Hoffman came up with. And that all of space-time, everything that's going on is just constant, is just these little agents talking to each other. And notice that these are really, really simple little agents. Okay, so here's the 2 agents talking to each other. And what we're going to do is say, let's assume that this creates space-time. So we'll start by calculating how much time it takes to move information around this loop. And then we'll calculate how much space light can traverse. So we imagine they communicate using light. Going around that little loop, how far is it from here to here? Since these guys are creating space, we can say anything we want, right? They don't exist in space, so we can say that their interaction creates space. And we can ask, how much? How much space does it create? And that'll give us a size for a voxel, and we can calculate how much energy this takes, and pack that much energy into that little voxel, and then say, okay, if we had enough voxels to fill the universe, how much energy would we have? So I won't, drag you through all of this math, but we can do this, and I'm going to assume that each of these little agents has to encode 4 bits. And the reason is that that allows me to tie this model in a way that I yet don't understand to particle physics. So that's at least a motivated assumption. But if you make that assumption and just run through all this arithmetic, it turns out that it takes 1.5 picoseconds for information to travel around this loop. Now, that's a long, long, long time. Right? 1.5 picoseconds is a lot longer than, say, 200 femtoseconds, which is the response time of rhodopsin. But we're talking here about deep space. We're not talking about a place where there's lots of stuff going on. We're talking about a place where there's the minimal possible stuff going on. So maybe in deep space, time has a little bit different meaning than it does here, where there's lots of stuff happening. So if we plug in the speed of light, with that 1.5 picoseconds, we can calculate a distance that gets generated by this exchange, and that distance is about 1/10 of a millimeter. So if you hold your hand out about like this, and move your fingers together till you can just see the gap between them, that's about 1 millimeter. So 1/10 of a millimeter is a big distance. It's much, much, much bigger than the cells in your body. So again, maybe things are really different in deep space. Maybe deep space doesn't look like the space here. So if you calculate then how much energy this little cycle packs into that little voxel, you get a number, and here it is. And that number may also look familiar because it's almost exactly the same as the number we got last time. So we can calculate the cosmological constant this way too. And we get a number that's almost the same as the last time. And the only similarity between these two ways of doing things is we've assumed that observers are everywhere. The first time we didn't assume anything about what the observers were like. The second time we did. The first time we assumed something about what the observers were observing. This time we didn't. The only thing we assumed in common was that observers were everywhere. And we get the same number for the cosmological constant. Well, that's really weird. What does it mean? I haven't the faintest idea. And you can take these calculations and extract from them lots of interesting predictions about physics. And they suggest that what physicists call grand unification might actually happen. Because if you take the temperature really far up, it predicts that the force of gravity gets stronger and stronger and stronger until it's almost the same as the strong nuclear force, which is what grand unification means. It also suggests that supersymmetry might be true, although supersymmetry's never been observed. You heard about it a little bit yesterday from John Hagelin's talk. It's a particle theory concept. But this model suggests, okay, there's a reason to believe in supersymmetry based on this kind of calculation. But basically, I don't know, is the answer. But it suggests at least that if we make precise assumptions about what it means for consciousness to be fundamental, it actually has some implications for physics. And if that's true, that would be really interesting. So, thanks.